Welcome to The Explainer. Today, we're going to break down one of the most crucial services on AWS, Elastic Load Balancing. Honestly, if you're building anything that needs to scale and be reliable, this is something you just have to get right. So let's dive in.
Okay, let's paint a picture. You've launched your application, and guess what? It's a huge hit. That's awesome, right? But then the traffic starts pouring in, and suddenly your app slows to a crawl, or worse, it just crashes. So what do? How do you handle all that love from your users without everything falling apart?
Well, the key here is something called load balancing. It's really all about automatically spreading out that incoming traffic across multiple targets. Think of it like a really smart traffic director for your application, making sure no single server gets buried under a mountain of requests. So let's really dig into what load balancing is, because it's pretty much the foundation for both scalability and high availability.
Okay, so Elastic Load Balancing, or ELB, is AWS's managed service for this. It's essentially a traffic controller on steroids. It stands in front of your application and distributes all that incoming traffic across, say, your EC2 instances. And it can do this in one or even multiple availability zones, which is super important for reliability. But we'll get to that in a bit.
All right, so this is where it gets really interesting. AWS doesn't have a one-size-fits-all load balancer. Instead, you've got a whole family of them, and it's all about choosing the right tool for the job.
First up, you've got the Application Load Balancer, or ALB. This one works at layer 7, the application layer. You can think of it as the really smart one. It's perfect for HTTP and HTTPS traffic, because it can actually look inside a request and make routing decisions based on the content. So if a request is /images, it can send it to your image servers, and if it's /API, it sends it somewhere else. Super powerful for web apps and microservices.
Then we have the Network Load Balancer, the NLB. This guy operates at layer 4, the transport layer. The name of the game for the NLB is pure, raw speed. We're talking extreme performance, super low latency. It's built for TCP and UDP traffic, where you just need to move packets as fast as humanly possible. Think gaming, streaming, any workload where performance is king.
And last but not least, the Gateway Load Balancer, or GLB. This one is a bit different. It operates way down at layer 3, the network layer. You use the GLB when you want to deploy, scale, and manage a fleet of third-party virtual appliances. So think things like firewalls or intrusion detection and prevention systems. It lets you inspect all your traffic without having to completely re-architect your network.
And this chart really lays it all out beautifully, right? You've got the ALB at layer 7 for your web apps and microservices, the NLB at layer 4 for high-performance, low-latency stuff, and the GLB at layer 3 for those third-party virtual appliances. Choosing the right one really depends on what kind of traffic you're dealing with and what you need to do with it.
Okay, so now that we've met the players, let's talk about how we actually use them to design for high availability. How do we build architectures that are truly resilient to failure?
Well, it really starts with understanding the shared responsibility model for resilience. See, AWS is responsible for the resilience of the cloud, the physical data centers, the hardware, all that good stuff. But you, the customer, you're responsible for resilience in the cloud. It's up to you to build a workload architecture that can handle things going wrong.
And the number one way to do that? Building across multiple availability zones, or AZs. An AWS region is made up of multiple isolated AZs. You can think of them as totally separate data centers. So, by deploying your application across multiple AZs, you protect yourself from single location failures, like a power outage. And here's the magic. Your ELB is smart enough to know this. It will automatically route traffic only to the healthy instances in the AZs that are still up and running.
Now, let's talk about cross-zone load balancing. When it's enabled, traffic gets distributed evenly to all your registered servers, no matter which AZ they're in. If it's disabled, traffic only goes to servers within the same AZ as the load balancer node that received the request. Now, for application load balancers, this is on by default, which is great. For network load balancers, though, it's disabled by default, and if you turn it on, just be aware it does incur some charges for that inter-AZ data transfer.
Okay, so we've got our load balancer, we've got our multi-AZ architecture. Now let's move from theory to action and talk about some key reliability practices.
All right, this is super important. How your clients actually connect to you. First, you need to use and respect DNS. Don't let your clients cache the IP address of the load balancer for too long. Why? Because it can change. Second, if a connection fails, always refresh the DNS and resolve the hostname again. And third, if you're retrying, please use exponential backoff with jitter. You don't want to accidentally DDoS your own service when it's trying to recover.
And then there's just some good old-fashioned housekeeping for reliability. Consolidate your ELBs when you can. For instance, in EKS, you can use ingress groups to share a single AOB. It just makes things simpler. Definitely monitor your services with Amazon CloudWatch so you know when things go wrong. And maybe most importantly, configure your health checks properly. This is how the load balancer knows if a server is sick and needs to be taken out of rotation. Get this wrong, and you'll be sending traffic to dead instances.
But look, even in the most perfectly designed architectures, stuff happens. So let's wrap up by troubleshooting one of the most common errors you're going to run into, the dreaded HTTP 502.
Oh yeah, the HTTP 502 bad gateway. If you've worked with web apps, you've seen this. And the first question that should pop into your head is, who's to blame? Is it the load balancer, or is it my application behind it?
Well, finding the source is actually pretty straightforward if you look at your CloudWatch metrics. Here's the deal. If the HTTP code _ELB _502 count metric has data points, that means it's the load balancer. But if you see data points for the HTTP code _target _5xx count metric, well, then the problem lies with your target application. This one check tells you exactly where to focus your efforts.
And a really common cause for this is when the target closes the connection too early. It's usually because its keep alive timeout is shorter than the load balancer's idle timeout. Think of it like this. The load balancer thinks the phone line is still open, but your application server has already hung up. So when the load balancer tries to say something else, it gets an error.
All this talk about design and troubleshooting, it brings us to a final and honestly the most critical point from the AWS well-architected framework.
So your architecture is reliable on paper. It looks great in the diagram, but have you actually tested it? How do you know for sure it's going to work when things get real? You have to consider practices like chaos engineering and game days. I'm serious. You need to validate your recovery procedures before a real failure happens. It might sound a little scary to intentionally break things, but it is the only way to build real confidence that your system can handle a real disaster. So, here's the takeaway. Don't just design for reliability, test for it, prove it.